Today we're very pleased to have with us Yi-Wen Chiu, who holds her PhD in Water Resources Science from the University of Minnesota, and she now works at Argonne National Lab as a postdoc appointee. She's been studying water resources for over 10 years, focusing on management, sustainability, and future scenario modeling. Her interest in water resources started in 2000 when she worked as an assistant researcher in the Water Environment Research Center, National Taipei University of Technology in Taiwan. 4 years later, she has published the first textbook in ecological engineering in Taiwan, chaired more than 10 national and international conferences in water management and ecological engineering, and was one of the top instructors of the National Ecological Engineering Training Workshops. She also participated in drafting Taiwan's national mandates in watershed conservation, ecological engineering, implementation, and land use planning. Dr. Chiu's doctoral study focused on water energy nexus, stimulating multi-scale water resource future based on different scenarios of climate change, demographic trends, and energy policies. In 2009, Dr. Chiu published a top-cited article related to ethanol water footprint in the journal E&T. She currently participates in research on estimating and quantifying water footprint of biofuels at Argonne, with broad interests related to water sustainability and its environmental impact assessment. She's also recognized by the international communities and was invited to participate in the Life Cycle Analysis Working Group under the United Nations and the draft comment on the latest ISO on standardizing water footprint calculation procedures. As I mentioned, Dr. Chiu received her PhD from the University of Minnesota. She also received her master's from there, and her bachelor's was in the Department of Forestry from National Taiwan University. So we're very pleased to have her with us here at our sustainability seminar today. Dr. Chiu, thank you.
Thank you, Nancy. That's exactly the reason why I want to get a PhD degree, just so someone would call me Dr. Chiu. I kid you not. It's just that after working at Taiwan for so many years, without a PhD degree, people just had to call me, Miss Chiu, Miss Chiu. And somehow I'm just like, there's something missing over there. So that's why I quit my job and decided to move forward and get a PhD degree over here. As Nancy just mentioned, I spend most of my time at University of Minnesota. And I love it there. People complain about the winter, but Minnesota gives me a real fall season, and that's the main reason why I love it so much. And after I moved to Illinois last year, well, it's pretty similar. It's still in the Midwest region, but climate-wise, it's slightly different. So I still miss Minnesota, but I try to love Illinois here. And I don't know how many of you have heard about Argonne National Lab, or have you been there? Been there? Okay, great. Argonne is a very interesting place for doing research. It's primarily funded by DOE. That's why I had to put a logo down here, the Department of Energy. And we got most of our fundings directly from DOE. And that's why we have all kinds of divisions working on energy-related topics, from fundamental science, chemical engineering, material science, all the way to decision-making supporting division like energy system division that I'm working with right now. So our division is slightly different. We try to support DOE in terms of finding the right pathway to sustain our future energy, and also not to destroy, of course, not to destroy the environmental qualities and ecosystem balance. So that's why Argonne also put out this special division to support this kind of service. And I moved to Argonne for almost 1 year already. And this project that I'm going to present it to you today actually has been done in the past year, and that's the primary task that I've been focusing on. So today we are going to talk about the water footprint embedded in different type of biofuels generated by using different kind of feedstocks. And we want to see in different feedstock pathway and how that respond to different water scenarios. And we want to see how we can connect energy and water together. So as you know already, since early 2000, at the end of 1990s, ethanol and biofuel start to get a lot of attention across different communities, like science and policies and even local public organizations and NGOs. And it's because we do have this energy demand, but on the other hand, we strive to balance the environmental loadings and try to see if there would be any environmental consequences related to this kind of energy development. So as we started to notice that since last decades, we start to see a large-scale biofuel feedstock productions, and people start to talk about what kind of environmental impacts would be potentially associated with that, and how we can deal with that. And on the other hand, we also notice that there is not just producing biofuels that simple. It actually requires all kinds of inputs, from natural resource, from additional power, additional electricity, additional land, and even can be more or less affect our urban development as well. And all these impacts, yes, we do see on-site impacts, and sometimes these kind of impacts might occur hundreds of miles away. Let's say, the fertilizer used or associated with the corn stover at Midwest region. It might have some consequential impacts related to at the Gulf of Mexico. So how can we put all these topics together? How can we fit all these topics into one picture? We need a specific framework to combine all these subjects. So that's why the water and biofuel the combination of water and biofuel start to gain our attention. And our group has been working on this topic for a couple of years already, even before I started working with this division. And last year, we tried to establish a standardized calculation framework in order to compare different feedstocks side by side. And we want to see how these feedstocks will respond to different scenarios. So if we want to do that, we need a very specific framework to quantify these kind of multiple pathways. So we want to start with quantifying a freshwater footprint associated with cellulosic and advanced biofuels. And we want to see, regional water demand or county level resolutions, how this kind of spatial resolution will affect this, the numerical results. So we classify all the water demand into blue, green, and gray water. Any of you heard about that? Yeah. Personally, I'm not a big fan of coloring water. Water is supposed to be transparent. It's supposed to be clean. And if you tell people, this is blue water, this is gray water, people are just going to freak out. But it's just that scientifically we need a term to classify different water pathway. We need to classify different water combination embedded in one service or one product throughout the life cycle perspective. So that's why we decided to go along with this kind of general classification of different type of water. The blue water, it actually accounts for the consumptive irrigation and also the refinery process water loss throughout the entire system. And the green water is the part of crop evapotranspiration that's satisfied by precipitation. So that's naturally occurring, and we we can't really directly, well, indirectly, yes, we can change that pathway, but directly it's primarily governed by natural forces. And the gray water is a little bit different, and I noticed that many people actually have a hard time understand the term gray water. Blue and green water, these two type of water, they account actual water volume associated with like crop growing demand and the processed water demand. But gray water is actually a virtual volume. It's not actually the volume that we use to dilute the pollutant. It's a volume equivalent terminology that we use to quantify the water impact associated with water pollutant. And the pollutant primarily is from like agricultural practices and also the refinery process if it occurred. So this is not actually the volume we use to dilute the pollutant. It's just a quantitative term that we use to represent the magnitude of the impact. But together with blue and green water, that's the total water footprint that most of the people are talking about here. And we choose different pathways to practice this kind of framework. And right now, the candidates include corn stover, soybean, wheat straw, wheat stalk, and algae. And the system boundary could be vary. For some scientists, they even include like electricity water demand, or the water demand associated with fertilizer production. But here, the primary part is still related to feedstock growing stage and also the refinery production stage. So we focus on this specific system and try to compare different feedstock side by side. This chart gives you a snapshot how we compute the entire process. The computation start with regional data that we collected from NOAA or USDA related to climate, land use, or agricultural data. And these regional and local data are fed into our inventory, and together with the simulated results that we get using agricultural hydrological model, for instance, like SWOT modeling. And we also have a different process to adopt regression analysis as well to establish this specific water footprint data inventory. And the data will further move on to our integrated assessment stage. Here, we primarily use evapotranspiration modeling or a crop growing modeling to do all kinds of assessment. And then all the water demand would be breakdown for different stage, processing stage, and also for different feedstock. And here, there's an important assumption here is the water allocation. Water allocation, that means we have to further classify water between the feedstock itself and also the water embedded in the residue. So we apply the harvest index to allocate the water volume between different materials. And at the refinery stage, we also deduct the co-product water credit to account for the water saving or the like power displacement credits. And for algae, we will talk about this in detail later on. Algae, we assume it's an open pond raceway type of facility, and it has a closed system nutrient cycle. So this is the exciting part, the result. These charts, the most important thing is to see how spatial resolution would affect the numerical results. I know there are all kinds of studies and reports out there. They try to quantify, how much water is associated with a different type of feedstock, and they all come up with different numbers. And sometimes, if you compare different studies, they actually have huge different results that has been published. But here, I think the most important factor that distinguish different type of numerical result is because of the spatial resolution. For instance, the chart gives you a upper value and lower value on the county level. And the yellow bar here represents the national average. And as you can see, blue, green, and gray water, no matter what kind of water, you actually see a significant shift from the top value down to a lower end. It's because of the weighting factor caused by the primary producers like corn producers or soybean producers geographically. So that's why, as you can imagine, if a specific project or any future projection is done based on national average, it actually tells nothing on the local scale. So if we, in the future, refinery studies actually requires a lot of local environmental assessment. And this is a number you can see how different they are actually on the national average and county level. So for instance, stock, the green water embedded in wheat stock actually ranging from almost just a trace all the way up to over 2,000 liters per kilogram dry mass. So that's a huge variance. And for blue water, in general, blue water, the variance of blue water is lower than green water. It's because the blue water is if you still remember, that's the part the part we have to apply like irrigation to satisfy the crop growing stage. So in general, that represents a smaller fraction during of the crop growing demand. And the gray water, it accounts the water we require to, yes? Biomass, the dry mass. No, it's a dry mass. So the reason why we start with the dry mass is because we realize that the biofuel water footprint, actually the primary water footprint is associated with the crop growing stage, comparing with the refinery processing stage. So there is almost 80% or 70%, depends on what kind of feedstock that we're talking about. It's about 70 to 80% of the water footprint actually is contributed through the crop growing stage. So that's why we started with the dry feedstock here stage. Yeah, thanks for bringing up that question actually. And as you can see here, soybean requires almost no fertilizers comparing with corn or wheat, and that's why you see a very, very low gray water associated with the feedstock growing. And algae, that's a very interesting story later on. Algae requires no gray water because if you still remember, we assume it's a closed system of all the nutrient can be recycled entirely. So that's why there is no further gray water. That's an important assumption here. But in general, the green water shows a bigger variance than the blue water. And this is just a horizontal, is a vertical view of the number. And we will break it down to different geographical distribution for you here. So let's start with the conventional biofuel feedstock, which includes the corn stover, soybean, and wheat. It's just because the scenario assumption between the conventional feedstock and algae is totally different. So we cannot really compare them side by side under the same chart. So we start with the conventional feedstock here. And not surprisingly, actually, the Midwest will contribute most to the feedstocks. We are the corn belt here. And we assume that we will use about 30% of the corn annual production here. That's about the current ratio right now. About 30% of the annual production is used by the refinery. And for soybean, we also assume it's about 12%. That's about the same level right now. And for corn stover, we assume it's a 24% removal rate, and for wheat, we assume it's a 30% removal rate. And the reason I think many of you might have already known is because of the soil conservation. We cannot entirely collect all of them for soil conservation. So we can only use a fraction of the stover or the wheat stalk. And with this kind of assumption, it contributes to over 678 billion kilograms per year. I know many people probably scratching their heads and wondering how many short ton that is. Yeah, units conversion is always a really big problem here, and just bear with me for a while. We are gonna use the kilogram instead of ton, and I try to put together like a liter, and how much gallon equivalent, but primarily we're gonna use the ISO system here. And so with that kind of acquisition assumption, it will contribute to over like 678 billion kilograms of dry feedstocks per year. And primarily is from for corn. So corn ethanol actually contribute to the 54% of the entire biofuel production on the annual basis, and followed by the corn stover. Soybean right now can only contribute to about 2% of the annual biofuel, and wheat stalk ethanol is about 15% based on the acquisition assumption here. So this is what the water footprint looks like. We start with the corn bioethanol. There are many ways to present these kind of numbers, but in order to give you a more consistent fashion, we decided to stick with how many liter of water would be required per liter of biofuel, or gallon per gallon, liter per liter. So that with that, we can easily compare different feedstock, and also the biofuel generated from different feedstock. So the blue water here, as you can see, for each gallon or each liter of ethanol, it requires from 2 to over 1,000 liters of water for irrigation and also for refinery processing. And for green water, it ranks about 20 gallon or 20 liter per liter to over 2,000. And you can see that this region, it received less precipitation, and that's why most of the agricultural practices still rely heavily on the irrigation. And that's why in these two charts, you see a complementary fashion. With the drier area, there would be less green water available for the feedstock growing. And where with the wet area or area applies a lot of irrigation, you will see a higher blue water proportionally. So that's why every time I'm really glad that I'm presenting this topic here at Midwest, because we don't normally use that much of irrigation water. And in 2009, when I published the first paper of the water footprint associated with ethanol, California people actually, they were very mad at us. And they were just like, how did you come up with that, that number? And it's not actually true. We use all the corn from Midwest. And we were just like, you probably don't want to go with that, because transporting all the corn from Midwest, that's actually required long distance of transportation. And we are talking about more carbon footprint, from that aspect. So there is, that stormed up a little bit debates and a little bit conflicts. But we're just really glad that this kind of study can draw a lot of attentions out there, and more attention means more discussion, more debates, but more thinking. So here in the Midwest region, we don't normally irrigate our corn that much. So that's why you can see only a trace of blue water associated with corn ethanol. And for gray water, now, do not say that we actually use 50 liters of water to dilute our fertilizer leaching. It only means that we need this much of water to assimilate the pollutant, from the legal level down to the background level. So this is just to give you an idea, how much impact and the level of the impacts associated with fertilizer application. And not just fertilizer. Actually, the number also governed by hydrological characteristics, climate characteristics, and even local soil characteristics, because the soil can control how much leaching would occur, at the downstream. And hydrology will define, how fast and, the magnitude of the fertilizer leaching as well. So that's why you can see a huge variance across the entire continent. And from the water resource perspective, corn ethanol sourcing about 32 liters of groundwater per liter of ethanol, comparing with only 6 liters of surface water. But on the regional or county levels, actually, the ratio is pretty similar. It's just because at the Midwest regions, the primary producers, we use a little bit more groundwater, and that kind of shifting the weighting down to a low 6 liter for the surface water. And for corn stover, corn and corn stover, the harvest index is about half and half. It's about 0.5. So supposedly the water footprint between corn stover and corn should be very similar. However, we still see a substantial difference because of the co-product credits that we were talking about at the beginning. And for corn, we apply a DDGS replacement and we get a credit from there. But for stover ethanol, we actually use a power displacement. So that's why at the end, on the refinery, after the refinery process, you still can see a difference between corn and corn stover ethanol. But still, geographically, the distribution still share the same fashion. So because you can see here, in general, the Corn Belt has a relatively low blue water embedded in per liter of ethanol. And here, there is only a trace of green water embedded within the corn stover ethanol. And for the gray water, it's pretty much the same fashion, it's just different magnitude. And the groundwater increase, the water sourcing increased a little bit to 70 liter per liter of ethanol. And for the surface water, you also increase a little bit up to 12 liter per liter of ethanol. And the total blue water requirement here, actually, that's highly depends on the production scenario that we are talking about here. But based on the 30% and the 30% acquisition rate, it's about 400 billion gallons per year of blue water requirement. And for soybean biodiesel, soybean only grow in the central and eastern region of the U.S. And the blue water ranking is still very low, all the way up to 1,500, slightly lower than corn stover and corn. And green water is actually higher; it's up to the over 3,000 per liter of ethanol, biodiesel. And for the gray water, also it's ranking about a trace to over 270 liters per liter of biodiesel, and primarily still sourcing from the groundwater as we expected. And this is the wheat stalk. Actually, wheat stalk is not yet been used for cellulosic bioethanol production, but we just want to see that the refinery can actually apply the similar technology to generate cellulosic ethanol using wheat straw, but it's just not yet been proposed to the decision makers to go for this pathway. But we just want to see with the wheat straw production that we have in the U.S., can it show a similar potential to contribute to the biofuel pool? So that's why we stick with this proposal and try to see whether or not it shows any advantage comparing with corn or corn stover. And it turns out that this western region, they still requires a lot of blue water for corn, for wheat stroke bioethanol, and the numbers on the county level is pretty close to corn stover as well. And the gray water is the performance of gray water is not as good as the soybeans, but it's still relatively close to what we observe from corn and corn stover ethanol. And from the water resource perspective, it used pretty similar fashion between ground and surface water, and it's just that we still source from groundwater a little bit more than the surface water. So this is an important chart just to show you if we put water demand into perspective and compare that with water supply, how the geographical distribution would look like. So we put together all the blue water demand because that's entirely depends on our agricultural practices, highly depends on our anthropogenic decision-making process, and compare with the available water. We define the available water here as the annual stream flow derived from the USGS, and we compare the water demand versus the water supply. And in general, all kinds of fuel generated from different kind of feedstocks, it requires less than 1% of the available annual available waters. However, we do see some hot spots around these regions. Do you know where that is? Do you know what aquifer that is? Yeah, Oklahoma. Yeah, there's Oklahoma aquifer down there. It's exactly the same location. So you get to see this kind of hot spot, kind of eye-catching racial distribution. And so the most important message here is that we know the government and local organizations, they put tremendous efforts to try to protect Oklahoma aquifer. But with the future refinery expansion, we want to deliver this kind of message and help the local decision makers how they can put this kind of water demand into their decision-making process and see if we can support and come up with a more advanced water conservation programs in the future. If local community, they have this desire to establish a refinery in these regions. But this kind of chart can give them additional insights in how the local water supply will respond to water demand. Yes.
Maybe you covered this before, but if I look at this map, let's take anything, a corn stover.
Yes.
Is the assumption that it's the same production all through the United States?
No, the production is based. The fraction of production is the same, but the corn stover production is different, based on local yield rate. Yeah, but we assume that we derive 20% or 30% of the local available corn stover, but the actual production, it depends on local yield rate, and the yield rate will be different, county by county. Yes.
1% is the cut point here. I mean,
no, it's just because I don't want to scare the audience. No, but it's just because most of the 99% actually will fall below 1%. There's no like statistic reason for that.
Or the highest, right?
The highest, I think, is 7%. 7%. Yeah, for some counties. Yeah.
It's only based on surface water flow.
The stream flow. So that also accounts for like base flow, from groundwater. So that is a final result of.
But if you're going to say that it's feeding an aquifer, wouldn't groundwater be part of the available water?
It's represented through the base flow. Yes. Yes. I mean, eventually, not immediately, but eventually it will contribute part of the base flow. Yeah. I mean, there are many ways that we can, associate demand and supply together. For instance, some people, they use effective rain as a indicator of how much water will be available locally, because that's the start point of all the water resource. And some people, they use the end point, like the stream flow. That's the end point assumption. And some people, they use the start point, for instance, like effective rain. So there are many ways to look at the available water here. But we just want to put the water demand into perspective and see the ethanol or all kinds of biofuel, the water demand associated with the biofuel, and try to compare that with what's actually available in the natural system. So are you still with me? Yeah. Now, algae. I don't know if any of you seen the algae study so far. Most of the algae studies, there are a couple of them try to quantify algae water footprint. But so far, there is only one study that actually covered the entire U.S. And most of the studies, I would say, it's more like they use a designated state as a case study, or they use a national average as a system, average system. But here, we start with a temperature. Solar radiation is a key factor determining biomass available from algae. And we found out that actually most of the high producers were located at the southern region because more sunlight available and suitable temperature range at this region. So we decided to stick with the 17 states that I mark in the red boundary here. And we move on to consider available land resources. For instance, we have to pick a slope less than 1%, and that has been proposed by some pioneer studies. They suggest that in order to build algae refineries, this is the bottom line. The slope has to be lower than 1%, and the minimal site requirement is about 490 hectares. That includes 400 hectare for the pond area, and the rest of the 90 hectare contributed to the operation facility. And we try to root out, for instance, like government-owned land properties, and we also root out populated urban area, of course. And we only select like shrub, grassland, or pasture hay as available land. And so far, most of the study, when they try to project future algae biodiesel production potential, they stop right here. They look at the climate constraint, and then they look at land resource constraint and try to project what's the potential. But in our study, we take one step forward and look at the water stress at a local scale. And we try to see how water stress can shape our future algae biodiesel production potential. So we create a couple of different scenarios, and one is without any water constraint. That would be similar to the top two layers. But if we apply additional constraint, for instance, like water stress less than 0.4 and also water stress lower than 0.2, the reason why I took these two numbers is because these two numbers has been proposed by the United Nations as a threshold defining the magnitude of the severeness of water stress. So if any water stress index lower than 0.2, that means the stress is considered low stress. But between 0.2 to 0.4 is considered mid-high water stress, and over 0.4 that would be classified as severe water stress. So that's how we create this threshold here as a scenario criteria. And we also look into what's the available municipal wastewater as an alternative water resource other than rainfall for the algae biorefinery. So these give you some idea. Here, if we stop at if we stop at this level here, if we just consider climate, solar energy, and we consider the available land cover, this is a number we can get within the 17 states, about nearly 40 million acres within the 17 states. That accounts about 4% of their land area. But if we talk about the sustainable land area, which means we factor in the water stress, then you can see the area size will significantly drop down to 1 million acre, or about 5 million acres under the water stress of 0.4 or 0.2 scenario. So that's the magnitude of how much the water stress can affect the bioenergy, the algae biodiesel production potential here. And of course, many people argue that, right now we don't really have a market-size refinery out there, so there are all kinds of technical assumptions associated with this kind of production projection. For instance, lipid content, it ranks from 10% to 80%, actually. It depends on what kind of algae stream that we're talking about. But in general, most of the study, they stick with like 20 to 25% or 30% as an average. And the harvest efficiency, not during the pound collection and harvesting stage, not 100% of the biomass can be collected. There will be some loss. So we have to factor these kind of efficiency factors into account. And operational water loss, most of the studies, they assume evaporation loss only. They assume this is going to be a closed system, and there would be no additional water required to make up other loss. However, the number here, there are two papers so far try to quantify how much water associated with operational loss. That includes like blowdown or maintenance. Sometimes we need to clean up an entire tank in order to control the toxicity level in the pond. So the number here ranks about 0.15 all the way up to 0.5 cubic meter per square meter of the pond per month. So that's about the number that we can get so far. And so on the county level, the biodiesel production potential is from the 0.3 per liter per square meter of the pond all the way up to about 2.5, 2.6 liters per year. And on the blue water perspective, it ranks about 11 to over 2,000 liter per liter, which is very close to corn stover. Yeah, it's very close to corn stover in the same region. And the green water is slightly lower than other feedstock as well. So these give you a snapshot how much the water stress can affect the production potential. So if we look at the business as usual scenario, that means we only care about land availability, we don't care about water stress, then the counties that can actually contribute to accommodate the refinery actually is up to about 550 counties within the 17 states. But if we set the threshold, the water stress threshold down to 0.4, actually about 132 counties would be disqualified into the production line, and about 150 counties that would require to reduce their capacity as well. So that's how much the water stress can shape the entire production potential. And on the refinery count, like if we count the sites suitable for refinery establishment, it will drop significantly from over 31,000 all the way down to 7,000. That's the magnitude that we're talking about here. So as you can see, and the MWW, that means municipal wastewater. So without municipal wastewater, or with municipal wastewater is the alternative water resource plus the precipitation, it cannot really shape the production of the biofuel potential, and it actually didn't contribute much to the effect of lowering water footprint. Many people were hoping that, by reusing the wastewater, maybe we can significantly reduce the blue water requirement. However, the impact is not that significant, which was a little bit surprising to us at the beginning. But later on, after we looked through all the data and tried to, screen out all the step-by-step, we found a reason. And I'll give you a detailed information at the end. But the water stress under this scenario, the water stress is lower than 0.4, and we reuse the water footprint. Reuse the wastewater. The blue water footprint accounts about for 81% of the entire water footprint. That means only about 20% of the green water contribute to the entire water footprint. So that means these contribute to the evaporation that's satisfied by rainfalls, and it's about 250 liters per liter of biodiesel. And these also give you a breakdown of the contribution and composition of the blue water. Here, the evaporation is about 413 liter per liter of biodiesel. And the biggest part actually is the operational loss, including blowdowns and maintenance and everything other than evaporation. So this is kind of surprising, actually. And it's different from other conventional biofuel. Conventional biofuel, the operational loss is only very low, like corn ethanol is only about like a 3.6 to 4.5 liter per liter. But here, the algae biodiesel is actually over 400 liter, 700 liter per liter. And the municipal wastewater only accounts about 13. So if we add up these two parts and deduct this part, it gives us a net blue water over 1,000 liter per liter on the average of these 17 study regions. So you can see that the production of the biodiesel would drop significantly down to these two levels, about 50 billion liters or 25 billion liters per year. And corn stover actually falls in between here, in between these two scenarios. The corn ethanol production, with our assumption, like we use 30% of our corn available in the market, that would give us about 35 billion liters of ethanol, comparing with these different scenarios. So this is why the wastewater cannot really significantly contribute to lower our blue water footprint. It's because we put some constraint here. First of all, it needs to be temporarily available. That means we are not going to build additional wastewater storage for this refinery. So whatever is treated this month will be available for the refinery this month. But if it's out of the growing season, let's say in the winter or early summer, that the refinery is not operating, then the wastewater will be gone. It's not going to be available temporarily. And also, not all the wastewater quality can be used by the algae. It has some limitation. So we can only choose the wastewater that has been processed with the secondary treatment practice, and that will give us the bottom line of the acceptable water quality for algae pond. And also, right now, the municipal wastewater actually has been reused by some of the downstream sectors. For instance, there are some existing industries, they reuse the wastewater treated from the wastewater plant. And also partially of the wastewater can be used by the agricultural irrigation as well. And that is happening right now. So in order not to have any consumption conflicts with other sectors, we choose only the wastewater that currently been discharged to surface water body. That means no one is using them. So we pick that kind of volume here and assume whatever is treated locally would be reused by the refinery within the same county. So there is no cross-boundary transportation of the wastewater. Yes?
Your refinery refers to an algae
Algae pond, yeah, algae refinery.
growing up there.
Yes, yes, yes. So as you can see here, the green dots that indicates where we can actually accommodate the refinery, algae refinery. And the blue dots indicates where the wastewater is available. And you can see a mismatch between these two sectors. And that's why actually only very minimum of the wastewater can be used by the algae refinery on the local scale. So that's the reason why we didn't see the blue water get reduced significantly after we use the wastewater. So here gives you a number. If we pick the temporarily available wastewater for the algae refinery, actually it accounts about 80% of the suitable wastewater discharged in 2008. In 2008, in the 17 study areas under the original business as usual assumption. That means there is no water stress. There is no water stress constraint, and about 80% is temporarily available. But geographically, only the 42 out of these 80% is geographically available on a local scale. So that means only 33% of the total wastewater is actually usable by the algae refinery. That accounts about 2.4 thousand billion liters per year. And if we factor that in with the algae refinery blue water requirement, it only accounts about 1% of the algae blue water. So that's why it only represents a very small portion in the water footprint. And that's exactly the reason why we didn't see a significant reduction after we factor in the wastewater credits for the algae. So the take-home message here is that we are not trying to do a winner-take-all kind of scenario and say that okay, this type of feedstock and this type of biofuel is definitely better than this type of feedstock and biofuel. The most important thing is that to look at the geographical distribution of the water demand and see if we can strategically select the right pathway for local biorefinery development and expansion. For instance, Northeast region, we break down the entire continent into 10 agricultural divisions. And Northeast region, Corn Belt, Lake states, they are pretty okay of producing all kinds of biofuels. However, if you are a decision makers from the Delta states, you probably don't want to promote too much over the soybean biodiesel. And this is the strategic development that we are talking about. We are talking about how we can do a better site selection that reflects the local natural environment characteristics and soil characteristics and even climate characteristics. So for instance, here for southeast regions, maybe we can pick soybeans, biodiesel, and the wheat stalk as a primary promotion biofuel. And for the northern plain, probably not such a big fan of corn stover bioethanol here. And for algae biodiesel, the biggest challenge still relies on the operational loss that we were talking about, because right now there are only two numbers that has been presented out there, through the scientific analysis, and we don't know exactly how much of the operational loss can be decreased in the future, throughout, like a blowdown, like and like the biomass drying, there will be some loss evaporated that cannot be captured or reused. Yeah, so that or leaking, like the tank leaking, that kind of loss, any kind of loss other than evaporation. Yes, if ideally, that will drop down here. It will be, yes, it will be way more acceptable, by comparing with other feedstock. Yeah, but that's still the biggest challenge right now, because we don't know exactly if we build a actual refinery, like algae refinery out there, how much water would be required. Yes. So in the future, these algae water, this only accounts blue water. So in the future, the algae blue water might be significantly decreased, throughout the technology improvement or like the system efficiency. If we can generate or produce more biodiesel, on the per acre basis, then of course this number will be decreased again, correspondingly. Yes.
This is my question. Is it possible to grow algae in salt water?
Yes.
If in salt water, right, we can considerably decrease probably the below water probably usage.
It depends on the system design, because for the salt water, it just represents the different water source. So for operation, we still expect a certain level of water loss through like blowdown or like pipe leaking, pond leaking or evaporation. So it just represents different water source. Yeah, but from the engineering perspective, maybe the blowdown ratio would be different because it's salt water comparing with fresh water. Yeah, so there are some chemical process embedded with this kind of discussion as well. But yes, that also depends on the algae strain that you select. Yes.
Considering the potential of recycling the water.
That's net consumption. So we only, that has been taken into consideration already. So without talking about the recycling, that would be the total withdrawal. But here it represents the net consumption. Yeah. Partially, right now they assume the recycling rate is about 80 to 90%. So there would be still, about 10 to 20% of water loss. Yes. 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 So in the future, maybe like you say, if we improve that part of efficiency, yes, it's possible. It can also contribute to lowering the algae blue water here. Yeah, it's one of the key factors as well. Yes. Not in this presentation, but we are working on two publications right now, and that will be part of the discussion. Yes. 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 Yes, yes. So that's why the most important message here is that we are not trying to say, algae is better or worse than conventional biofuel. Yeah, it's just that, put into the geographical perspective, we have to make the right decision how to select, the right pathway that can sustain not just energy, but also water resource in the future. Yeah, so I think that's a key point here. But of course, like you say, there are, especially with algae, there are all kinds of technical uncertainties embedded here. And that's why when we are comparing a different feedstock, it's always important to look back and see in the report what kind of technical assumption that they're using right here. For instance, like lipid content. 25% to 50%, that means we can double the production already. Yeah, so it really varies significantly, actually, yeah. So I hope are we running out of time? Okay, yeah. So here, the key point of our study is that we want to take the local criteria into account and give people a more detailed perspective how water demand from the biofuel and the water supplies will be available on the local basis. In the a couple years back, in the Science Journal, they published a paper. They say water is just like politician. It's the local that counts. So that's why we try to break down the resolution and see how biofuel water demand would respond to different scenarios and water availability. So we try to determine what's the sustainable pathway, not just for energy, but also for water resources, as I mentioned. And we want to prioritize the regional target feedstock based on a local criteria, and also water demand, because right now most of the production potential is projected based on like economy and logistic analysis, and not so many people factor in water limitation into this kind of projection study. So we hope that this kind of study can bring more insights and give people more thinking to do in the future, and more brainstorming in the future. Thank you. Yes. Oh, I'm sorry. Water stress is a indicator that used by the United Nations. It factors in how much water we draw over how much water is available. Yeah, so it's a fraction between water consumption and water withdrawal and water availability. Yes. Right. So yeah, that's another way to compare, different feedstock and their efficiency in water consumption as well. Yes. No problem. Thank you.